Okay, just one more minute of patience. Our speaker
Hello, sorry.
is down. Fantastic. Okay, so we can start. So good afternoon, everyone. Welcome to the NITheP mini school. My name is Francesco Petruccione, and today we have the pleasure of hosting again Dr. Sahal Yacoob from UCT, and he will deliver the second lecture in his series on Introduction to Elementary Particle Physics. Yeah? And if I remember correctly, the topic of today is some introduction to particle physics calculations. So Sahal, and sorry, and maybe just as a kind of announcement, unfortunately, we skipped last week's lecture, but we will add 1 week at the end of the planned series, so that the last lecture of this mini school will be the first Tuesday in September, and then we will start on the second Tuesday in September with a further mini school, and luckily. September has 5 Tuesdays, so we will keep the rhythm going. So Sahal, please, thank you very much. I will stop sharing the introductory slides, and now you can take control of the screen and start presentation.
Great. I'm just getting my screen share. Okay, can everybody see my slides?
Yes, thank you.
Okay, great. So welcome back. Thank you for coming back. I'm sorry about last week. And let's jump right in to an overview of the calculations. So just by way of introduction, and immediately a typo on the first line of the first slide is maybe not the best way to start. But to test a theory, of course, we want something measurable. So we're going to go through, in a very hand-wavy way, how to go from the theory depicted here by a Feynman diagram, which are one of the things we're going to talk about today, and compare that to the data from an experiment. And here we see a plot showing us some decent agreement between data and experiment for some random data. Don't worry about the details too much. The major things we depend on for this at this level are the Feynman rules, which are a set of rules that allow us to look at a diagram like this and immediately skip ahead multiple steps in a calculation, just from some simple rules that are repeated all the time. And that's because of the relatively simple structure that the standard model has. We spoke about it last time. There are just 4 fundamental forces. There are the 4 force carrying particles, and everything else has to work within that. The things that we calculate and then can compare to measurements are decay rates. So it's the probability that a particle will disintegrate, and cross sections, which are essentially an understanding of the interaction between the particles, or it's a way of measuring the probability of interaction between the particles. And there's a whole slide on that. We'll talk about that in more detail. And here is that slide. So the cross-section gives us an effective area for an interaction, and it's proportional to the probability of the interaction to have a particular outcome. So we know probabilities must add up to 1. So if we add together the various cross-sections of something, and then we divide the cross-section for what we're looking for by that. So if we're looking for a particular process, let's say A plus B goes to C plus D, and we calculate the total cross-section for A plus B for something to happen. So that's my notation for something to happen. the probability of A plus B to go to C plus D. Let me see if I can write this in a way that's useful. So the probability of A plus B going to C plus D is equal to the cross section of A plus B to C plus D divided by the cross section A plus B going to everything, where X is just the unknown. And so that's, in that way, the cross section is proportional to the probability. It's not exactly a probability. It has dimensions of area, and it's important to note that an individual particle does not itself have a cross-section. It's the interaction between two particles that has a cross-section. The standard units we're going to use, or that we use in particle physics, are bonds, which are 10 to the minus 28 meters squared. Seems like a bit of a weird unit. It's so small in terms of the SI units. We measure things in particle physics. The amount of data we have is in inverse bonds, and the LHC is at the inverse femtobond level. So the cross sections we care about are quite small, and because of that, we use this very small unit called a bond. So here's another explanation from hard scattering. We can extend the idea of a cross-section to a differential cross-section. This is hopefully revision from classical mechanics for all of you, but if we have some little element d sigma here that is going to interact with our hard sphere, and this incoming particle is going to be scattered off at a particular angle theta, then the probability of particles coming in at d sigma off into the solid angle piece d omega here, which is a piece, a solid angle piece of the hard sphere, we call d sigma d omega. And we care about differential cross sections because we can get more information. And that might seem counterintuitive because the cross section is all the information, and the differential cross section is kind of one step less, right? If you look at this, you would think, well, sigma is equal to the integral of d sigma d omega d omega. And in this way, like, the integral looks like it should have more information, but really the cross section is just, and it doesn't have dynamical elements. But when we look at the differential cross section, which I have written out here, this will in general have some dependence on the angle theta, and then we can move our detector around and measure the differential cross section at different angles and get different data points that we can compare to our theory. So two different theories, for example, may give the same integral, but give different differential cross sections. And then we would care about that. So the more variables we have in our measurement, the more we can test between different theories and ideas of physics. I'm just going to flip over the slide. The slides are up for you to look at. This is to get an idea of just the hard sphere scattering cross-section, and the idea that at the end of the day, if you consider a point scattering of a hard sphere and you were to calculate the full cross-section, you would end up with just the area of the circle visible to the beam. I'm not going to say too much more about that unless there are questions afterwards. The other side of it, and I've just realized I feel like I've been rushing, so I'm going to take a deep breath and try to slow down. The other side of this from my point of view, is the luminosity. So the luminosity in our case is not the brightness like it is for a light bulb or for the sun exactly. It's the flux of particles. So it's the number of possible interactions per unit area per unit time. And if you remember, the cross section was in units of area. So if we take our units of area and multiply them by our units of inverse area, inverse time, we get the number of interactions of a particular type per unit time. So what's important here and might be confusing is the luminosity tells us the number of possible interactions, things that can happen, right? If we think about it in terms of statistics, it's the number of coin flips. The cross section is something that is defined for a particular process. So if I take the cross section for a particular process, let's say the number of times two protons collide, they create a Higgs boson. So we have our two protons, they collide, they create a Higgs boson, and then that Higgs boson decays to two photons. Let me be a thing. Then we would use, if we want to calculate the number of these events we're going to get, we would take sigma pp Higgs gamma gamma, which is something we can calculate. Obviously, I didn't get all of my dinging devices. And if we multiply this cross section by the luminosity, we'll get the number of this type of process per second. And then if we integrate that over time, we'll get the total number of events of that type. Okay, so the cross section is process dependent. The luminosity tells us about the number of possible interactions. And then this final term here, the integral of the luminosity with time, is often called the integrated luminosity. I know, very imaginative. Okay. And that is our measure of the amount of data we have on tape. So when we record data, we measure it in terms of the integrated luminosity. And again, if you go back to my idea that the luminosity is the number of coin flips or the number of coin flips per second. When you integrate the number of coin flips per second, we get the total number of coin flips in our data. So that's how we talk about our data. Here's a little practice problem for those of you who want to do a practice problem, and I can flip the answer up at the beginning of the next talk. It's pretty simple. The biggest problem is taking care of the units, how you deal with an inverse femtobarn and a millibarn. Then we have to talk about decay rates. So most particles decay. There are many particles which exist, and by particles, generally I mean bound states in this case. The only stable particles that we have in the universe are the electron, the photon, and the proton. And of course, when I say electron, I'm including the positron as well. There are a slew of other particles. A lot of them are bound states of quarks. Decay, here's an example of two decays. The first one is the J psi, which is a bound state of a charm and an anti-charm quark, decaying to an electron-positron pair. The second one is a muon, decaying into a muon neutrino an electron, and an electron antineutrino. When a particle decays, it doesn't care how it was produced. So all particles, once they're produced, decay exactly the same way. So the probability of a muon decaying in any particular piece of time is absolutely independent of when the muon was created. We have a decay rate then, the number left in this example at time t is the number at time t0 times e to the minus gamma t, where gamma is the decay rate. Particles can decay in several ways. So here we have the j psi going to e plus e minus, or the j psi going to, sorry, I really wanted to get that dinging turned off, the j psi going to mu plus mu minus. So there are different decay rates for each of these processes, and the total decay rate for any particle is the sum of each of the individual decay rates, and it'll change the total number of decay channels. So the number of this number n for the gamma i's will change depending on the particle we're looking at. Brightness, the mean lifetime of a particle is often just called its lifetime. It's the inverse of the decay rate. And the branching ratio is the fraction of the decay in a particular channel to the total decay rate. So this would be, for example, gamma j psi to EE divided by the sum over I gamma I for all j psi decays. And this just tells us the relative sizes of the different decay channels of a particle. So after we work through the details of the calculations, and a little bit about that going later, we end up with the cross-section for seeing a particular process being proportional to this expression. And this gives us a Breit-Wigner line shape. So I've jumped a couple of things here that we need to talk about. So I spoke about cross-sections as being the cross-section for going from some initial state to some final state. In the context we're talking about, our initial state is always some set of stable particles. They will interact, create some intermediate state, and that intermediate state decay the way we've been talking about to another set of stable particles. So in principle, we have stable particles, not B, we have stable particles of type A, and stable particles of type B, and in between we create something exotic and that decays. When we create that something exotic for the small amount of time that it exists, the fact of its existence is really given by it having a mass. So we have some new parameters in here. We've already spoken about gamma. This is the same gamma we've been talking about. It's the decay rate of the particle. This other new parameter we have is the mass of the particle. So when we create these intermediate states, for them to kind of exist, they have a defined mass, and then the cross-section for having them be created and then decay depends on their mass. and their width, this gamma particle. And so when we look at data, we'll see something like the shape on the left with a peak at the value of the mass and a width that's described by this gamma parameter. And on the right, we see real data. This is production and decay of Z bosons at the Large Hadron Collider atlas. So let's look at what we're talking about. We're plotting here the number of events with an invariant mass as a function of the invariant mass of 2 electrons. Now, the Z boson has a characteristic mass, which is mz equal to 91.188 GeV. And so if we look at our line shape expression, as the energy of this pair of electrons, this electron-positron pair, approaches this number, this term in the denominator gets smaller and smaller and smaller, and we head up towards a peak, and we'll hit our peak the mass of the Z boson. So when we talk about these particles having masses, when I talk about the mass of the Z boson, the mass of the W boson, the mass of the J psi particle, I'm actually talking about this parameter in this expression. And that means that when we collide things, when we have interactions at exactly this amount of energy in square root S is the invariant mass. So if you take any kinematic system of particles, write it out in 4-vector notation, add those 4 vectors together, you can always calculate an invariant mass. And that's what we're drawing here. And when the invariant mass is around the mass of the Z boson, start seeing lots more Z bosons being produced. And the width of this distribution is governed by how quickly the Z bosons then decay. So if a particle is stable, this becomes incredibly thin, becomes a Dirac delta function. That's why an electron, for example, has an incredibly well-defined mass. And then as particles are unstable, so the more exotic particles, they'll have different channels they can decay into, different branching fractions, and they get wider. So the exotic particles that we study often in particle physics are unstable particles. They're created and destroyed when we have these collisions. The wider the peak around their mass, plot the invariant mass of their decay products, the more unstable they are, the narrower the peak, the more stable they are. So how do we do all of those calculations? This is Fermi's golden rule, or the second golden rule, and this includes the Born approximation. The Born approximation is the idea that we have plane wave solutions. So the Born approximation is that our wave function psi of r of t is equal to something e to the minus I omega t. That doesn't need to be another e up there. Plus k dot r. So that summation, which basically we have these psi's that are the free particle solutions far away from the interaction, and the interaction takes place at a particular point. Then the physics part of the interaction is described by the integral of the final state wave function, the initial state wave function, and the perturbing potential. And then we have a term for the phase space. So we can combine all of these things together to get the interaction rate. The reason these are separated in this way is because this term, the amplitude term, tells us if the particular interaction is physically allowed. So if I wrote down an initial state wave function that was just an electron, and I wrote down a final state wave function that was just a positron, we don't see that in nature. So in terms of the interactions of nature that we represent with our potential, this integral would be zero, because otherwise we'd be violating charge conservation. We'd have a negative charge becoming a positive charge, and nothing would happen. So the amplitude term contains the physics, the application of conservation laws. Can a particular thing happen in terms of our knowledge of the interactions of nature? All of that is encoded into the amplitude. The other part of that is the phase space. So the phase space contains the information and basically enforces that the energy coming in must equal the energy going out, the total momenta coming in must equal the total momentum coming out. And in this case, this is just a little pictogram to show us two incoming particles with 4 momentum, PA and PB. Something happens that's allowed by the physics, and we have 2 outgoing particles with 4 momentum, PC and PD. So this is the way we think about all our interactions in the first place as 2-to-2 processes. 2 particles coming in, 2 particles going out, and generally we try to describe the world in terms of this language, and using that in the following slide. So generally, A and B are the 2 incoming particles, C and D are the 2 outgoing particles. So with the Born approximation and some assumptions that we work with spin averaged amplitudes, because when we calculate the terms in the matrix element, we have to take into account spin conservation. Then there's basically 2 lectures at the honors level worth of work, and we get to a description of a 2-body decay. A 2-body decay is just a decay that we've been talking about. So for example, what I used earlier was a J psi going to E plus, E minus. So in this case, that's A, and then B and C. So we can generically say that for any 2-body decay, the decay rate is this term that comes from the kinematics, because the kinematics are always going to be the same. There are some assumptions that are hidden in here, particularly what frame we're in. So P here is the momentum of either of the outgoing particles, and this is evaluated in the rest frame of the parent particle. If we have one particle decaying to 2 others, we have complete freedom into which inertial frame we use, and the easiest thing to use is the rest frame. So what's on the bottom here is the total energy in our initial state, which is just the mass of the particle. And this momentum is the 3 momentum, the magnitude of the 3 momentum of either of these particles in that same frame. So this is all the kinematic bits. And then the matrix element term here will tell us if the thing we're trying to calculate is actually allowed. And that's where the physics is. If we look at a 2-to-2 scatter, it's somewhat similar. We have a constant term. We have the bit that tells us about the physics. We normalize it by the energy squared. But since we have an incoming state of two particles, we can't be in a frame where both of those particles are addressed, because if both of those particles are addressed, they're not interacting, they're not scattering. So we have each of their energies individually that we add together. And then we have the 3 momentum of the initial state and the 3 momentum of the final state. And again, we're using, should probably write this down. This is in the rest frame of A, and this is in the center of mass frame of A plus B. So those are our 2 special frames. And now what is left for us is to talk about the thing I've been ignoring most of the time, which is the most important thing, I think. Well, some people think conservation of energy and momentum is important. The matrix element, the bit that tells us all about the physics. So this matrix element term is calculated most properly in quantum field theory. Remember, quantum field theory reconciles special relativity with quantum mechanics, but can also be calculated directly from the Feynman rules. So we're going to go through a little bit of the Feynman rules, because if we look at what I've told you so far, for example, any 2-to-2 decay, all of the terms except the matrix element squared are exactly the same. So there are some complicated mathematical integrals that we need to work through. But once you do that once, that's it. It's done. For all 2-to-2 decays, this is the expression. And then the details between looking at different integrals are in this element M. So we calculate probabilities from theory. We measure number of events, and then we can combine them. We've seen this earlier. Yes.
Do you want me to ask you some clarification questions now, or should we just leave them to the end?
No, I think if the questions are things that people need answers to follow along, then we should definitely do them now, because if people are lost, then there's no point in continuing.
Yeah, because that's also what I think. Sorry, ones are related to the kind of previous slide. So just to confirm, M is the total mass energy decay product.
On which, on this slide? On
no,
this
I think
slide?
in a couple of slides before.
Is it this slide, golden rule for decay and scattering?
No, I think it was before as well. I think it's where you have a, yeah, somewhere here, yes.
So, okay, so what is the question?
Just to confirm, M is the total mass / energy of the decay product. Is it correct?
This, yes. So it is, well, the invariant mass of the 2 decay products.
Okay. And also question related to the same slide. Does the height of the peak also indicate the likelihood of the decay?
Yes.
Okay. So
yes. So if I can just talk about that a little bit more than just saying yes. This, if we look at this data for the probability for what we measure, right? You can see that we have fewer events here and more events in the peak. And so, yes, at this value, the probability of getting events at this particular point is that much higher, right? If we take the ratio of the peak to this point, that'll tell you the relative likelihoods.
Okay, so there is one more question which are related to the curves, and is, can you get a very exotic particle with almost a flat curve?
So they can be quite wide, but if it's, that's an interesting question. So if it's flat enough, it doesn't exist, I guess. And that would be very interesting to look for. And then we can have a longer discussion about what it means to exist, right? So how big a peak does a particle need to have? As an experimentalist, my answer would be, I have no idea how we would find something like that directly, but I'm not sure of any actual limits on the continuum, right? So as gamma gets bigger and bigger and bigger, the particle gets wider and the peak gets broader. And so I imagine, yeah, as it gets broader, it comes down a bit and just flattens out. And I think these two parameters are essentially independent. So yeah, I mean, we get into a philosophical discussion about if it is flat,
what do
then
we
it's
call particle? Yeah.
it exists at all masses. I think that's my answer actually, right? That the existence of a particle is defined by it having a well-defined mass. And so the broader the peak, the less well-defined the mass is, the harder it is to think about it or talk about it as a particle. And so a particle, often we want to, sorry, I'm still going. Often we want to think of it as something that can propagate. And in quantum mechanics, things propagate in the eigenstates of the Hamiltonian, which are energy eigenstates, and energy eigenstates eventually translate to mass eigenstates. So if a particle doesn't have an invariant mass peak, then it doesn't really have a mass eigenstate, and to talk about that as a particle.
Okay. And on the same slide, the formula, is this expression empirical or theoretical?
Theoretical. So you can get this, any standard particle physics or relativistic quantum mechanics textbook will take you through this and give you this line shape.
Okay.
And so you have to assume an interaction, but this is what we get. There's included in getting the Breit-Wigner line shape are elements of special relativity.
Okay, and there is questions on some theoretical aspects. You have mentioned Born approximation. What is the approximation? Which thing was exactly approximated?
Oh, wrong way. The approximation is that we can describe the universe in terms of plane wave functions that are non-interacting. They're far away from the interaction potential, and that the interaction potential only acts over a short range. And so when we want to calculate the amplitude, we can say we have initial states that are essentially eigenstates of the vacuum, right, of a non-interacting Hamiltonian, and final states that are eigenstates of a non-interacting Hamiltonian. And then we have a small region of space where there is an interaction. And we can describe the universe by building this up. The counterpoint to that, right, if there was no approximation, then the answer is something like electromagnetism, for example, is a force with infinite range. And then you'd have to include the electromagnetic potential throughout the whole universe and solve that for eigenstates and figure out the interactions. And that becomes much more difficult to do as a calculation in my understanding. So the Born approximation is that we have these 3-particle plane waves and that the interaction takes place over a short space.
Okay, but again, for those who's interested, yes, in any standard scattering theory, it's explicitly explained what is the Born approximation is. So, okay, and the last question on the same slide, I assume, is does the rho in the formula contain any ambiguity, like a global phase or something like that in quantum mechanics?
No, we're about to talk about phases in quantum mechanics if we get there. I realized why I started out as if I was running a sprint, because we still have a few slides to get through. But in terms of phase space, this is just energy and momentum. It's not the phase of the wave. It's really just information about energy and momentum.
Okay, in that case, let's go to the Feynman diagrams. Thank you.
Right, so I think I was here. I lost my flow a little bit. Okay,
yeah,
so
you on this slide, yeah.
We have our Lagrangian or our Lagrangian density, and from our Lagrangian density, we get our equation of motion, which is the Dirac equation. The solutions to the Dirac equation are our 4-component spinors that we spoke about in the last lecture, where we got particles and antiparticles. And now we can talk about the phase of the wave function. So the phase of the wave function is the imaginary part in the exponent, and that's completely invisible to us. So if I go back to standard quantum mechanics, when we calculate a probability, our probability is equal to the integral psi stop psi d3x. Sorry about my handwriting. And so because that's the complex conjugate, that bit goes away. And anytime we want to do any calculations of observables, we have the imaginary bit going away. So anything we measure can depend on the phase. So the phase is basically the statement on the slide I'm going to read out. The Lagrangian should be symmetric under phase transformations. So if I change my wave function by changing the phase a little bit, my Lagrangian should look exactly the same. Because if it doesn't, then that means my physics is changing. And if my physics is changing, then I am sensitive to this piece that is actually hidden in terms of how we do the calculations. So when we test this and we throw in, you just take every place there's the wave function, you add e to the I alpha to the wave function, you plug that into your Lagrangian, and you see that your Lagrangian changes. Your Lagrangian, initial Lagrangian minus an extra term. So there's an extra term. That's not symmetric. That's not cool. We don't like that. So we add an extra term to the Lagrangian to account for this. So this bit is the initial Lagrangian, or part of the initial Lagrangian. Here we go. It's up here. And then we add this extra term where a mu has to behave this way. And if we do that, then when we do this change, right, we change the phase of psi by some random amount on x. Correspondingly, a mu changes in this way, then we get the same Lagrangian out. So then we have an invariant Lagrangian. And this seems kind of random. Like, why would we do this? Why do we care? It's broken, it doesn't work, we're just adding epicycles onto epicycles. And that's a reference to the basically the heliocentric model of planets in the solar system. But what happens when we look at this term, we can very easily identify it with the electromagnetic interaction. So this term has 4 components, right? The new bit in this term is A mu. If we look at our standard Lagrangian, gamma mu was in there, psi's were in there. Term is A mu, and suddenly we have an extra constant, which is a degree of freedom. This A mu is a 4-component object that has to transform in this way. And further investigation of this, we find that these 4 components, the first component is essentially could be identified with the electromagnetic scalar potential. The other 3 components can be identified with the electromagnetic vector potential. And then this other constant is written in as E. That should have been your guess, if you're not reading far ahead of me. And we can essentially use this extra term, which we plopped in to fix the Lagrangian needing to be invariant under local phase transformations. We can use that term to fully describe electromagnetism. It didn't have to be, right? There's some freedom. A mu had to satisfy this equation, and there are other ways of doing that. And this constant didn't have to be the charge of the electron, but we needed a term like this, and a term like this can be used to describe electromagnetic interactions between positively and negatively charged particles. Once we've developed that, we get another term that describes a free photon. And this is the full electromagnetic Lagrangian. So the pieces of this Lagrangian are the mass of the charged particles, the kinetic energy of the charged particles. So this is just the energy of the charged particles, and interaction with photons, which is the electromagnetic interaction, and the energy of the photon field. And that's all we need to describe quantum electrodynamics. I still have many slides to go. Will we schedule for 45 minutes or for an hour? Ilya?
Sorry, Sahal, I was muted. For an hour, including questions, and of course with plus minus a reasonable error margin.
Okay, good. I think I will stop me in 5 minutes if I haven't stopped myself.
Okay.
I think we took some questions already. So this interaction term, where is it? This interaction term includes a photon field, a particle, and its antiparticle. And that can be described in terms of the Feynman diagrams. So here we have a Feynman diagram with an electron absorbing a photon and becoming an excited electron. Here we have an electron emitting a photon and continuing on as an electron. And here we have the Feynman diagram for 2 electrons bouncing off each other by exchanging a photon. So this vertex is always described by this term, where the psi bar is not always an antiparticle. We always have time flowing from left. On the lepton line tells us whether we have a particle or an antiparticle, and this goes back to what we spoke about in the last lecture about antiparticles being identified with positive energy states going backwards in time. And the vertical axis really doesn't have much physical meaning, right? At this point, we're not saying the photon and the electron are actually physically closer together. All that matters is that we started with a photon and an electron, they interacted, and afterwards we just had an excited electron. In terms of a full interaction, there's often an unobserved particle exchange, which is called the propagator. So if we look at the first half of the diagram of an electron and a positron scattering off each other, we get something like this, right? The second half of the diagram would be just filled in there, and we'd have our initial and final states. And if we look at this and try to conserve form momentum, we can do this in the center of mass frame of the electrons. So we will have for the E minus, we will have the 4 vector P E minus equal to, let me clear that up, sorry. So we will have the energy and momentum, and then P E plus is equal to the energy minus the momentum, where the energy is equal to the square root of m squared plus p squared. And since both particles have the same mass, they'll be the same. If we add these together, we get, this implies P gamma is equal to 2E0, and this implies that we have a photon with mass equal to 2E. Photons are supposed to be massless. So this is something called a virtual particle or an off-mass shell particle. And this is where we get into some of the details of the difference between the physical free particle measure, like the photons that come out of a light bulb, versus the photon as a propagator or a mediating particle for a force. So if our photon doesn't have its physical mass, it has some other mass, that is okay as long as it's inside the Feynman diagram. It's internal to the Feynman diagram. Particles like that are called off-mass shell or virtual particles. All propagators are virtual. All initial and final state particles are real. And even though this can violate energy conservation, that's okay as long as we only violate energy conservation for a short amount of time. I was going to take you through the calculation that shows that depending on the mass mediating particle, we can control the range of the force, but I think we will have to leave that for next week. Yeah, thank you very much. I'm sorry I was too optimistic about the slides for this week, and we'll adjust that for next week.
Yeah, Sahal, thank you very much. I think this will be a nice point where to start next week when we are again fresh and happy to absorb very quickly again new material. Ilya, I think there are still a few more questions.
Yeah, I think there is a still clarifying question from India who is asking, does Born approximation also means locality?
For the interaction, yes.
Okay.
So the interaction happens over a short space of time.
Mm-hmm. Okay, so there is one more question from India. You have shown 3 Feynman diagrams for the same interaction. How does one interaction term represent so many different Feynman diagrams?
Where have I shown 3 Feynman diagrams for the same interaction?
probably on the previous slide.
This is 3 different interactions.
The last slide. Right. Just
okay, let me. Yeah, sorry, it's not updating. What I'm looking at is different to what you're looking at. I have. Are you still seeing range of a force?
Yes.
Yeah. Yes.
Yeah, so I have changed what I'm sharing to be something else, but it doesn't seem to be updating. Let's try again. Hang on, let me change things. Okay, there we go.
Mm-hmm. Yeah, for
So
example.
that's the one with 3 Feynman diagrams that I've shown, but these are all different processes.
Okay, yeah.
We will, just to let you know, we will see different diagrams for the same process, and we'll talk about that in the next lecture. So the next lecture will probably be more theory and less about detectors, because you can describe the same process with different diagrams.
Yeah, because I think what he's wondering about that so many diagrams could be essentially represented by only one term in Lagrangian.
Well, that is, so the term in the Lagrangian describes the allowed vertex. And then we play with combining the vertices to get the full set of interactions. But we will talk about that more in the next lecture. That is where we were heading. And so we'll start there next time.
Okay, that's it on my side.
Okay, then if there are no more urgent questions, Sahal, thank you very much again for another very nice lecture. And you see the participants are already waiting for the next one to learn more about this chapter of your lectures. And I assume you will make the slides available again so that people might have the opportunity to review the material or to watch the video again before next week. So Sahal, thank you very much again. Ilya, thank you for moderating the questions. And I hope to see you all again next Tuesday at 2 p.m. So thank you very much for being loyal participants in this mini school. And have a good week and stay safe. Yeah, thank you very much. Thank you, Sahal. See you next week.
Thank you very much. Thanks everyone for your very good questions. Take care.
Bye.
Thank you. Bye-bye.